My name's Andrew Sornborger from Los Alamos, and this is joint work with Alpha Renner, Forrest Sheldon, Anatoly Zlotnick, and Louis Tao. I think Alpha is on this call. He did the lion's share of work on Luihi. And this is implementing backpropagation for learning on neuromorphic spiking hardware, and in particular on Luihi. Because this is a lightning talk, I'm going to give you the punchline first. Essentially, we have MNIST running, so 10-digit categorization on Luihi. We're getting validation of about 92%. So using a 3-layer network, takes about 14 Luihi time steps per training sample, and inference is done after the first 3 time steps. I'll describe more about this network afterwards. We're getting throughput of about 1,000 frames per second, so 1 millisecond per sample, and 0.3 millijoules per sample is measured on with probes on Luihi, and we have an energy delay product of 0.3 microjoule seconds. This is a plot showing the convergence of accuracy over epochs of training. Okay, so given that you've got the results now, I'm going to go into some of the structure of the network we put together. As people who have been kind of following what our group has been doing over the past couple of years, we've been pushing towards getting this working. And now we feel that we've got, a system that's scalable and working pretty well. We use a number of neuronal and network mechanisms for implementing this algorithm. We try and implement a fairly faithful an algorithm that's faithful to the standard mathematics of backprop. In order to do this, we use SynFire-gated SynFire chains. These are for organizing the information and controlling the propagation of information on the chip, as well as controlling processing and implementing things, for instance, like short-term memories. We use what we call push-me-pull-you pairs, which are just encoding real numbers with 2 neuronal populations. One population that encode it if it's positive, one that encodes it if it's negative, and they work in concert to encode the full number. We're able, using SynFire-gated SynFire chains, to gate ReLUs, and we can additionally gate the derivative of ReLUs using conditional gating pulses. This is possible because the derivative of a ReLU is just a theta function. We can implement Hadamard products just using one-to-one connections neurally. And then additionally, and this is important, the SynFire-gated SynFire chains allow us to simultaneously gate information to pre- and post-synaptic neuronal populations in order to implement Hebbian synaptic updates. This is important because it allows us to turn on and off learning and to regulate how the synapses are being modified over time. So people who are familiar with backpropagation will be familiar with this. This is just a single layer. There's not even a hidden layer here, but it gives you a bit of an idea of how it works. The idea is you have input. It propagates through synapses to an output. The output's compared to a target, and then the error is computed as this value delta here. And then due to the mathematics of backprop, you also need the derivative of the activity function for the output values. And then those combined in this way give you the update for a synapse between X and O here, the input and the output. In order to implement this, we use gating in order to, like I said, gate the information where we want it and when we want it. So in our network, we have a couple of, what I think of as registers. X, the input would come into this register. It then gets gated through a set of synapses to the output, as well as being stored in a memory in this population here. At the same time, we gate in the target value. This is supervised learning. And then we gate the output and the target through synapses that compute the difference, which is the error. The memory is shuffled over to another population, and then we, again, using gating, gate the information that's needed for the update simultaneously to this layer, the input and the output layers here, so that via Hebbian learning, the correct update occurs at the synapses. There's a technical issue in that we only have positive spikes. We can't have negative spikes, and therefore, if we want to decrease the value of the synapses, it has to be done in a different way than increasing the values of the synapses. So here, this shows how we do it. We have an input, it goes through synapses to an output. We gate the target in, and then if the target is greater than the output, then the computation gives us a positive result in this error population here, which is gated to a memory population. And then in this later phase, the red phase, we have, again, simultaneously input and output are on two sides of pre and post synaptic sides of a set of synapses. And so we get a Hebbian update. If the output's greater than the target, then we send the error is sent to a different error population, and then we implement a depression phase. So we have to set up, because of this, not being able to have a negative spikes, we have to separate into two phases the updating of the synapses. Things get more complicated when we go to a multi-layer network. So here, this is a 3-layer network with one hidden layer, O1. You see that we have two sets of synapses we have to update. We also have a transpose of the second set of synapses that we have to update as well. We have two sets of derivatives and so forth, but all of the mechanisms that you need in order to implement any multi-layer backpropagation algorithm can be implemented using the mechanisms that I've discussed here. This shows you how information in a 3-layer network propagates. So the different neuronal populations or identities are here on the y-axis. On the x-axis is time. And you can see here we use a gating chain up here in order to direct the flow of information. We gate the input through a hidden layer to the output. That's this feed forward box here. We then do the comparison in this error box. Derivatives of the activity function are in this encoded in this conditional gating chain. And then all of this is combined in this backpropagation box, where I show both the potentiation and the depression phases for updating the synapses. So the first thing that we did here was just to really put a baby network together in order to learn the XOR function. Excuse me. So here, before learning, you can see the T is the target, O is the output of the network. And you can see that there's no very good correspondence here between these. On the other hand, after learning, there's nice correspondence. So we can do quite well with XOR, which we should be able to. And now I'm back to MNIST, which, as I said, we get 92% validation. It's a 3-layer network. We've downsampled in the first layer to 10 by 10 as opposed to the standard 20 by 20 MNIST digits. And as well, we take our neuronal populations actually just to be individual neurons. So we've effectively binarized the circuit. This gives us, again, an energy delay product of 0.3 microjoule seconds, roughly plotted on this plot. These are just preliminary results. We're hoping to do a little bit better, but roughly on this plot that Mike Davies and Intel have put together, this is roughly where we show up in terms of bang for your buck on Loihi. So in conclusion, we put together a proof of principle pulse-gated spiking backpropagation algorithm. We use Synfire-gated Synfire chains to route and form memories. We also use it to control Hebbian learning in 2 different phases for depression and potentiation of synapses. We use binary coding for MNIST and with population rate coding for XOR. And for MNIST, we get about 1,000 frames per second and energy delay product of 0.3 microjoule seconds. So thank you.